Hey, this is Horner, and these are the multiple choice questions for simple harmonic motion. The very first one, you'll notice that you have an object attached to a spring. It's oscillating horizontally, so that's left and right, and there's no mechanical energy loss, which means that there is no force of friction, so you don't have to worry about friction in this one. The other thing that they have here is they want to know which of the following is correctly represents the kinetic energy versus time graph for the same object over the same interval. One thing that we have to look at is this is a position versus time graph, and we want to go to velocity versus time. We know that velocity versus time then will give us 1/2 mv squared, which is kinetic energy, and this cannot be negative. So whenever you look at these graphs, just remember kinetic energy won't be negative. So A and B immediately you don't even need to worry about. If you come back up and take a look, you'll see that when your slope is 0, your velocity is 0. When your slope for a position versus time slopes down like this, and we know it's negative. The bottom it's 0 again, here it's positive, and here it is 0. So we just need to find out where the kinetic energy is 0, where the kinetic energy is big, then 0, then big, then 0 again. So if we look at this one, it doesn't start with 0, so it can't be this one. This one does, and it goes to positive, then it goes to 0, positive, 0. So D has got to be our answer. For the next one, number 2, an ideal rubber ball bouncing vertically on a hard floor does not lose mechanical energy. So it would just, you would start up here, you would drop it, it would bounce, it would come back up, it would drop, bounce back up, drop, and it would do that forever. So this motion is not simple harmonic. All of the following are reasons for this except the period of the motion depends on the amplitude. Okay, so that's true. The force on the ball is not proportional to the displacement. Well, that is also something that would match. The gravitational force is trying to restore equilibrium. That is not true. Okay, so this is one of those reasons that is the exception. The equilibrium position is not at the midpoint of the oscillation. So there's another one. This is that ball. It does not lose mechanical energy. This motion is not simple harmonic is what they're saying. Alrighty. Let's go on to number 3. In number 3, you have a mass that hangs vertically. It stretches, and then if you try to do this same thing on an incline, you'll notice that this new stretch is going to be different. And because it doesn't have the full force of gravity anymore, instead it's just mg sine of the angle, your stretch should be less than x. So now we can get rid of c and d. So since these are both stretch is less than x, we need to look and see, is the period going to be less than t or equal to t? Well, t, remember, is equal to 2 pi times the square root of m over k. So we're not worried about gravity here. All we're worried about, since it's frictionless, is the mass and the spring constant. Well, our mass didn't change. So this has got to have an oscillation that is equal to t. So even though it doesn't go as far, it's going to go slower. But it will oscillate with the same period as the one that's hanging vertically. For number 4, oscillator 1 consists of mass 3 kilograms and a spring of a force constant of 100 Newton meters. The position versus time graph for that oscillator is shown here. Oscillator 2 consists of the same mass of 3 kilograms and the force constant is 400 Newton meters. So notice your spring constant is different. If both oscillators have the same total energy, which graph of position versus time is for oscillator 2? So if I know that k is 4 times as much and my x is half as much, my stretch is half as much, then I can say, well, t is going to be 2 pi times the square root of m over k. Here I'm going to have 1 over the square root of 4 because I've increased that by 4, so my period should be half as much. If my period is half as much, my spring energy, here I'm going to have 4 times a half squared, and that's going to be half. So here what we're going to do is we're going to say our period is half and our stretch is half. So our period now is half. So this period is long, this period is half as much. So we're going to go from here to here, there's half the period. This one is also half the period, but our stretch is also half. So we can't have as high of an amplitude. So our answer is C. For number 5, This one on another planet, the simple pendulum is constructed, and they plotted t squared versus L, which is a good thing, because if you have t is equal to 2 pi times the square root of L over g, you'll see that you can solve for t squared, get that L so it doesn't have the square root over it, and the slope of this then is going to be representative of 1 over g. Okay, so what we're going to do now is we're going to say, let's solve for g. So g is equal to 4 pi times the length over t squared. And if I plug all my numbers in, so I'm going to plug in my L and my t squared, okay? But I'm going to do that. I can't do it for all the points. I've got to think about what is the slope of this thing. So the slope is 10 over 1. And that's if I have t squared over L. But notice I don't. I have L over t squared. So what I did instead is I switched them. So now I have L is 1 and t squared is 10. So I just had to flip what was going on. In my mind, I don't have t squared over L. I have L over t squared. So I put the 1 first on top, put the 10 on the bottom. 1/10 of 4 is 0.4 times 3.14 times 3.14 gives you like 3.94. So it's really close to 4 meters per second squared, which is the right answer. The last one, a student measures the motion of a spring mass oscillator and calculates the regression equation based on the oscillator's motion. So all this regression equation junk here, if you've been in stats, you know what it is. It's just what we do when we do linearization. Same thing. And this equation, I know it looks weird, but if you look on your AP Physics equation sheet, you will see an equation very similar to this. In this equation, on the AP Physics equation sheet, when you take a look at that, you will see that that equation, and I'm going to grab one of these, is a cosine of 2 pi ft. Okay, so this is a cosine of, this is going to be 2 pi frequency times the time. So this guy right here represents 2 times pi times the frequency, and this represents the amplitude. Okay, so 2 pi f times t, this is also going to be the period of oscillation. So that's what you can look at. The time, you could even kind of think about period or time, same type of thing. The mass of the oscillating object is not in here. The spring constant, you see, is not in here. The fastest speed attained by that object, well, here's the deal. You do have a position and you have a time. And if you think about it, velocity is position over time. In this equation, you can find the velocity, and we've done that before when we looked at the different graphs. So if you go back up to the very top, okay, where you have to do these graphs, notice that you can go from position to velocity. And because you can do that, that also then allows you to look at this little guy right here and say I can also find the speed using this equation too. And that is the end of the multiple choice explanation for simple harmonic motion.